we have to define a function. So a relation is a function. So relation is anything that you can graph, when you're comparing two variables, you can graph points or lines or circles or shapes. So those are all relations. But very specific relations are called functions. And they follow the rule that for every x value, there's only one corresponding y value. So the example here shown here on this graph, because of this vertical line, there is an x value of 6, and that x value of 6 has two y values. It has a y value of 4 and a y value of 0. Because that singular x value has two different y values, this would be considered not a function. And I'm sure you guys remember vertical line test. I've made a video on that too, in that video's corner section. So please watch that video. And yeah, let's just quickly complete this. So where did it go? 1 moment. There it is. So solutions have been posted as well for you guys. Domain, simple definition, all possible values of x. Range, all possible values of y. And then we have domain and range for a specific example. Here we have a parabola. Domain is x belongs to all the real numbers, y belongs to all the real numbers, but y has to be bigger than or equal to 3. This is something we haven't gone over yet, which is the degree of a function. You should remember this, hopefully, or you should have done this in grade 9, and maybe you remember this, and that is the degree of a function. What is the definition of degree of a function? So degree of a function is always the highest exponent value on your variable. So in this case, our variable is x, and the highest exponent is 3. So this polynomial has a degree of 3. So you don't have to add or subtract or do anything. You just look for the highest number. That's it. An asymptote, hopefully you remember this from grade 11 as well. An asymptote is a point or is a line that a curve approaches more and more closely, but never touches. So this function or this curve is approaching the dotted line, but it is never actually going to touch that dotted line. And this function does not exist at that value. In this case, x equals -3. And the equation is y equals 1 over x plus 3. And the reason why there's a vertical asymptote is because you cannot divide by 0. So division by 0 is undefined. Therefore, the expression in the denominator of the function cannot be 0. Therefore, x cannot equal -3. This is why the vertical line is x equals -3. So the asymptote is x equals -3. And horizontal asymptote is similar to a vertical asymptote in that the function approaches the asymptote but never really touches that point. So for the range, there can never be a situation where the result of the division is 0. Therefore, the line y equals 0 is a horizontal asymptote. For all functions where the denominator is a higher degree than the numerator, there will be a horizontal asymptote at y equals 0. This is important. I'll repeat this. So when we're talking about rational expressions, this is from grade 11 once again. If I have a polynomial divided by another polynomial, we're going to get into a little bit more, but let's just say if I have something like f of x is equal to x squared divided by x cubed, then we can just write something like this. Let's just say we have something like this. In this example here, the highest degree for our numerator is 2. And the highest degree for our denominator is 3. And if we go back and read, this part here, it says for all functions where the denominator is a higher degree than the numerator, there will be a horizontal asymptote at y equals 0. So denominator is a higher degree. So in this example here, this is an example where the denominator has a higher degree than the numerator. So definitely there will be a horizontal asymptote at y equals 0. I'm not going to go over to the other rules about when the exponents are the same or when the numerator is bigger than the denominator. Those cases, well, in this case, you have an oblique asymptote, which this is the beginning of the course. We're not getting into this right now, but which we will learn either later on or that's in calculus I'm forgetting exactly if that's in advanced functions or calculus, but you will learn this eventually sometime in grade 12. And when it's a situation like this, you'll also learn that you take the ratio of the coefficients, and that is the horizontal asymptote. But once again, that's later on. So just wanted to cover that much. Okay, a polynomial function has the form this. This looks very, I don't know, strange, you could say. Very long and strange, but it's really not. It's exactly what I did here. I started with my highest exponent, x cubed, minus then I started the one less. So you always have to write it in order of, in order of greatest to smallest. So the highest degree term always is always written first, and then so on. So x cubed, then 2x squared, then 3x 1, and then the last term always is going to be a constant term, meaning there is no variable. And if there is no constant, then obviously it's just 0, but you don't have to write 0. So it'll just be like that. Anyways, so that's all that this is saying. They're just saying that there's a coefficient. A is just a coefficient, x is a variable, n is your exponent, and then a n minus 1, x n to the power minus 1, and so on. So n is a whole number, meaning 1, 2, 3, 4, 5, 6. Whole number, counting numbers. X are variable. The coefficients are real numbers. So a naught, a1, a sub 2, a sub n, whatnot are just coefficients, it's numbers in front of the variables. And the degree of the function is n, with the exponent with the greatest power of x. Yeah. A sub n is the coefficient of the greatest power of x, is the leading coefficient. So this is important. So this is some terms that you should know. Leading coefficient is the value that it is the coefficient that is attached to the highest degree. So in this case, my leading coefficient is 1 for the bottom polynomial, and for the numerator, my leading coefficient is 3. And then a naught is just the constant term, is the last term. So in this case, my constant term is 21, and in this case, it's 7. Very easy stuff. The range of a polynomial function, the domain of a polynomial function is set to a set of real numbers. And the range of a polynomial function may be all real numbers, or it may have a lower bound or an upper bound, but not both. And we'll talk about that. The graph of polynomial functions do not have horizontal or vertical asymptotes. So remember, we're just talking about polynomial functions. So these are different than other functions. And yeah, we'll get into the details in a little bit. The graphs of polynomial functions have degree of 0. Or, sorry, the graphs of polynomial functions of degree 0 are horizontal lines. So yeah. So an example of a horizontal line is if I just write y equals, say, 3. So y equals 3 is a horizontal line. That's all they're saying. Or like, another example, y equals 10, or y equals negative, 10, or y equals 100 or 99. So whenever y is equal to just a constant term, that means the variable has an exponent of 0. And because that's just 1, we don't write 3 times 1. We just write the constant term. So yeah. So those are all horizontal lines. Here's an example of polynomials that have an n value of 1, 2, 3, 4, and 5. So we have a linear function, y equals x, quadratic, y equals x squared, cubic, y equals x cubed, quartic, y equals x to the power 4, and then y equals x to the power 5 is quintic. So a power function is the simplest type, and that's just y equals a times x to the power of n. A is a real number, x is a variable, n is a whole number. So when I just said y equals x to the power of 2 or x to the power of 3, those are all power functions. They're the simplest type. Here we are going to determine which functions are polynomials, and then we're going to state the degree and leading coefficient. So y equals sine x, g of x is equal to sine x. Is that a polynomial function? Well, is that of the form like this? And it's not. You can clearly say that there's a sign there. So this is a trigonometric function. It's not a polynomial function. 2x to the power 4, this is a polynomial function. It has a degree of 4 and a leading coefficient of 2. As for c, this is a polynomial function. It has degree of 3 because that's the highest exponent, and the leading coefficient is 1 because that term has a coefficient of 1. Here is example D. Is example D an example of a polynomial function? And it's close. It does look like it, but it's actually not. It's an exponential function because the base is a number and the exponent is a variable. And for a polynomial function, the variable has to be the base. Here, we are moving on now to interval notation. So interval notation, hopefully you have seen this many times before in your, mathematical academic career in high school. So in this course, you will often describe features of graphs of a variety of types of functions in relation to real number values. Sets of real numbers may be described in a variety of ways. So we use an inequality. So this is important. Usually use domain and range. We use this inequality notation. We have -3 greater than x and then greater than or equal to 5. We have 2 interval or bracket notation. And this is important. So if you have a curved bracket, that means -3 is not included. It's not equal to -3, just like how in this example, there is no equal sign. So x is not equal to -3, but it is bigger than -3. So that's why I use a curved bracket there. And a square bracket is used to define that the value at the endpoint is included in your range. So in this case, 5 is equal to x. So therefore, we use a square bracket. So that's the kind of tricky part. But interval notation is just remembering to use either curved or square brackets. So just be careful with that. That's very important. And this is, inequalities. And then we have a number line, which, we don't really use number lines that often, but you should know them. And a open dot that looks like this is once again used to determine that the endpoint value is not included in the range. And a closed dot is used to inform people that that value is included. So it is x is equal to 5, and we use a closed dot. So these are all the different ways of describing, interval notation. All right, notes. Intervals that are infinite are expressed using infinity or negative infinity. So it would be something like negative infinity, comma, to infinity. And you always use round brackets for infinity because you can never actually have infinity as a value. Can't input it. Square brackets are indicated the end values. Okay, I just read this. Round brackets indicate the end value is not included. Round brackets is always used infinite. Okay, I just said that. So yeah, amazing. Okay, let's continue to example 2 now. Below are the graphs of common power functions. Use the graph to complete the table. So very basic stuff. Y equals x, special name linear, domain, range, just -infinity to infinity. End behavior. So as x goes to -infinity, y is going to -infinity. What does that mean? It means you start from the origin and you're going towards the left. And x is getting smaller and smaller and smaller. Hence, x is going to -infinity. What's happening to my y values? So my y values are also going smaller and smaller and smaller. So y is also going to -infinity. Another way to say it starts in quadrant 3. The graph starts in quadrant 3 and then it moves on to quadrant 1, ends in quadrant 1. So whenever we're reading a graph, we're always reading from left to right. And the end behavior when x is getting very large, so when x is getting larger and larger and larger, y is also getting bigger and bigger and bigger. So you say when x goes to infinity, y also goes to infinity. For quadratic functions, domain and range, very simple, -infinity to positive infinity. This function goes all the way to the left, it goes all the way to the right. It's good. As for range, this function goes all the way up, but does not go all the way down. So at what point does it stop going down? And that's the x-axis, or 0, when y is 0. And that's included y can be 0 in this example. So we use a square bracket to denote the endpoint for 0 is inclusive, and then infinity, then it goes all the way up to positive infinity. End behavior as x gets smaller. So what's happening in this function? When x is going to the left, it's getting smaller and smaller and smaller. What's happening to y? Y is going up, 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 up. So y is going to positive infinity, starts in quadrant 2. In this example, when x is going to positive infinity, so it's going to the right from the origin, it's getting bigger and bigger and bigger. What's happening to y? Y is also going up, bigger and bigger and bigger. So